Besides the addresses, we indicated that memory was divided up into ranges of addresses to represent different areas that the system would use. To understand these concepts easier, we will begin by looking at the historical systems that preceded the z/OS system so that we can see how memory usage has evolved. So in these early systems, memory was divided up into four distinct areas. The nucleus represented operating system programs that had to be memory resident and provided fundamental system services. The LPA, or link pack area, also represented memory resident programs, but often these programs were placed here for performance rather than as a requirement of the system itself. The SQA, or systems queue area, is used to hold control information that the operating system needs in order to manage the resources and work. After memory has been divided in this fashion, then anything left over could be used to run programs. From this we can see that if we have too much loaded or defined into our operating system areas and not enough RAM memory, then the amount of work we can run is significantly reduced. In the 1960s, the ancestors of z/OS were the OS-MFT and OS-MVT systems on System 360. Each represented a particular way in which program memory would be managed for the work that was to be run. The purpose in looking at these systems is to begin by examining the simplest implementations of memory usage and introduce some of the problems that existed so that we can develop a better sense of how various changes have addressed these issues over time. In the 1960s, these systems were all real storage systems. In other words, the operating system and work would run directly on the memory that was installed without any adjustments or control. These systems were all architected as 24-bit systems, so the maximum amount of memory available at this time was 16 megabytes. OS-MFT allowed the system programmer to partition or divide up the remaining memory into fixed sizes. So as work came into the system, it would run in one of the partitions. However, if the program was too big, then it might only fit into a particular partition that had been defined big enough. So even if other partitions were available, they couldn't be used. Also, if a program was smaller, then it would simply be wasting the space within a partition it was running in. In OS-MVT, this was modified to allow each job that was running to specifically request how much memory it was going to use, called a region. This seemed like a better idea, but one has to remember that when memory is assigned, it is assigned in one piece. So if I want 100K, then I must get it all in one chunk. So the problem here was that work would come in and request different amounts of memory, shown here with different colored areas, but as it ended and new work started, we would be left with holes in memory that could only be used by new work that was smaller than the memory that had just run. So as different work would run, we would end up fragmenting memory by having little holes that couldn't really be used by anyone, increasing wasted memory. In this example, we can see that when the region marked with an X has ended, only a job with a lower memory requirement can fit in this area. To resolve these problems, virtual memory was introduced. This idea of something being virtual is based on the concept of presenting a kind of image that everyone sees and works with, while the real hardware or function is hidden. In this way, anyone dealing with the system doesn't have to account for the behavior or requirements of the hardware. To implement virtual storage, real memory was divided up into 4K pieces called pages. Doing this allowed us to achieve two objectives in better memory usage.